So now we're going to start having a look at power of hypothesis testing. This is quite a large section. It is going to take us a while to get onto actually having a look at power. The power of a hypothesis, though, tells us how likely the result that we have found is going to be true. To be able to calculate this, we need to be able to find the probability of making a type 1 and a type 2 error. So that is what we're going to have a look at first. Now you may remember from AS we had a look at type 1 and type 2 errors, and you should have this table in your AS notes booklet. So remember that a type 1 error is when H0 is true, but in our hypothesis test we end up rejecting H0. And a type 2 error is where in reality H0 is not true, but in our hypothesis test we have ended up accepting H0. Now in A2 statistics we need to be able to find the probabilities of these. So these have two symbols which are alpha and beta. And as you can see here, alpha is the probability of making a type 1 error and beta is the probability of making a type 2 error. To be able to find the probabilities, we need to use the definitions of each of the errors. So alpha is easier to calculate of the two and control. The reason for this being that if we know what the significance level of our hypothesis test is, then alpha is going to be equal to the significance level. So when the null hypothesis is true and we reject H0, you make a type 1 error. The probability of making a type 1 error is alpha, which is the significance level of the hypothesis test. An alpha of 0.5 indicates that you are willing to accept a 5% chance that you are wrong when you reject H0. To lower the risk, you would use a lower value of alpha. However, using a lower value of alpha will also make it less likely to detect a true difference if one really exists. If we are not given the significance level, however, then we have to go a little bit further. This isn't like in the rest of statistics where when we've been looking at it, if we're not given the significance level, then we use 5%. Instead, we will be given criteria to which we would be rejecting H0, and we need to be able to find out what alpha is from that. So our first example is that Emma believes that the number of blue cars per hour in a car park happens at an average constant rate of more than 3.8. So from this, because we're talking about a constant average rate, that tells me that this is Poisson that they are talking about, even though they haven't specifically said so. So from this, I know that X follows a Poisson distribution with a lambda of 3.8. She decides to test this by counting the number of blue cars that come into a car park in a single hour. And again, here this was 1 hour, and now we're looking at another hour, so we don't need to make any change to this. She decides that if there are more than 6 cars entering the car park in this hour, then her claim is correct. So her claim was that it was more than 3.8, and now she's saying that if she finds strictly more than 6, then she is going to say that that claim is correct. Now this is also where it's slightly different to hypothesis testing, in the fact that it says strictly more than 6, so that means more than 6. If she gets 6, she's still going to be accepting H0. She's going to say that there's no change. So if we were to run a hypothesis test on this, our H0 would have been that lambda equals 3.8, and our H1 would have been that lambda is more than 3.8. So she's saying that if she finds, she's going to reject H0 when X is strictly more than 6. Now if we have a quick look back, a type 1 error is where we reject H0 but H0 is actually true. So if H naught is actually true, then that means that in reality, our mean is still 3.8. So we need to find the probability that she is rejecting H naught, given that the mean is still 3.8. And that's quite simple because that's how we usually find the probabilities in a hypothesis test. It's just what we're actually finding. This is not greater than or equal to because it says strictly more than 6 in the question. So if you have one of the new calculators, then we need to change this to be the probability that x is greater than or equal to 7. Remember, if you have one of the older calculators, you're going to have to change it to 1 minus the probability of x being less than or equal to 6. So in our calculator, we're going to dist across, this is a Poisson one, we're going into PCD, our lower is 7, our upper is a really big number, our lambda is 3.8, because we're saying that H naught is true, the lambda is actually 3.8. And that gives us that alpha, the probability of making a type 1 error is 0.0909. Remember, as I said before, if you do have one of the old versions of the calculator, then your x will be 6, your mu will be 3.8, and then you need to do 1 minus that. Let's have a look at another example. So here we have Brim believes that a coin is biased, so that heads comes up less than tails. Now here we're talking about two outcomes, heads and tails. If it was a fair coin, then we're saying 50%. However, he thinks it's biased so that heads come up less than tails. So that sounds to me like a binomial. Let's just keep checking because we haven't fit all the criteria yet. We haven't got a set number of trials. So he decides to perform a hypothesis test to test his theory, in which he tosses the coin 10 times. There we go. That's our set number of trials. So we've got x follows the binomial distribution with a number of trials of 10, and we're testing the probability of 0.5. And this is talking about heads. So because he believes that heads comes up less than it should, our H naught is going to be that P is 0.5, and our H1, if we were running a hypothesis test on this, would be that P is less than 0.5. So he decides that if less than 3 heads come up, his claim is correct. So again, it strictly says here, less than 3. So if he got 3, he would still be accepting H naught. So it's less than 3 when we are rejecting H naught. So we are told that we are going to reject H naught when x is less than 3. So we need to find the probability of this. And either one of the calculators that you are using now, we need to change this to the probability that x is less than or equal to 2. So the lowest that we can have is 0. The biggest that we can have is 2. Oh, sorry, I'm in the wrong bit. So we're in binomial this time, BCD. So the lowest that we have is 0. The biggest that we want is 2. Our number of trials is 10. And our probability is a half that we are testing. That gives us a probability of 0.0547. We put in that our H naught was true. We put in that the probability was 0.5, and we found the probability that we end up in the reject H naught region. So that is our alpha, the probability of making a type 1 error. Let's have a look at one more example before we go on to the now you try questions. So here we have Abdul believes that the mean temperature in July is 20 degrees C. Abdul finds out that the standard deviation of the temperature in July is 4 degrees C. So we have a mean, we have a standard deviation, that's screaming normal to me. Abdul decides to test this by measuring the temperature on a randomly selected day, and that if the temperature is less than 10 or more than 30, then he is incorrect. And we're trying to find the probability that he makes a type 1 error. Now, this isn't a very good hypothesis test to do because he's just testing it on one day. If he tested it on more than one day, we would have to be using central limit theorem. So please bear that in mind, that you do have to still use central limit theorem. However, in this case, our mean would still be, so applying the central limit theorem, our mean would still be 20 that we are testing. Our standard deviation would be 4 divided by the square root of 1, which of course can then just be simplified again to be 20 and 4 for our standard deviation. Remember, when you write down the normal distribution, it's actually the variance that you write in it, so just be careful there. If we were doing a hypothesis test on this, because this time we have two sides to this. We have if it's less than this temperature and if it's more than this temperature. So we've got two sides to be taken care of. So that means that it would have been a two-tailed test. So our H0 would have been that the mean was 20, and our H1 would have been that the mean was not 20. I just do this to bear in mind what it is that I would have been testing. So this time we are told that we're going to reject H0 if X is less than 10, or, and remember that when you're doing or, you add them together, X is more than 30. So we need to add the probability of these two happening together. Now you could do it separately. I'm going to show you first doing it separately, and then I'm going to show you a quicker way which I would actually use to do it. So we're going into dist and normal this time because this is a normal one. We're going into NCD. For the first one, we want less than 10, so our upper is 10. Our lower is minus a really big negative number. Our standard deviation is 4, and our mean is 20. So there we end up with a probability of 0.006297. For the second probability, the lowest that we want is 30. The biggest that we want is 999999999, a really big positive number. The standard deviation and the mean are still the same. And that gives us 0.006297 again. Might not always be like that, so do make sure if you're using this method that you find them both. And then we can add these together in the normal part of our calculator, 0.006297 plus 0.006297, and that gives us 0.0124 to three significant figures, and that would be our alpha. Now, if I was doing this in the exam, bearing in mind that this is the normal distribution, it's a continuous distribution, and the fact that here we're having to find two probabilities and then add them together, instead what I would do is I would use the fact that the probabilities are going to add up to 1. So here I found this probability and this probability, and I added those two together. The method that I am now suggesting is to find this probability, and because we know that the area under the normal distribution curve adds up to 1, we can just do 1 take away this probability. The reason why I think this is slightly easier is because then we're only actually having to use our calculator to find one probability. So if we're going to dist norm NCD, our lower would be 10, our upper would be 30, and this gives us, for our red area here, 0.9875866. So then straight away we can say that alpha is 1 minus 0.98758,056. We can pop that into the normal part of our calculator. So 1 minus 0.98758,056. And look at that, we end up with exactly the same answer to three significant figures, 0.0124. So it's completely up to you which method you decide to use. It's just that I find the second one a little bit quicker and more direct, but if you struggle to think of it that way, you're fine to find the individual probabilities and add them together. I would now like you to pause the video and give the Now You Try questions a go. So hopefully you've now given the Now You Try question a go. So here we have, Iona claims that the mean length of worms in her garden is longer than 8 centimetres. Iona finds that the standard deviation of the length of the worms is 4 centimetres. So that tells us that this first Now You Try question is a normal one. Iona chooses a worm at random. Again, this is an awful hypothesis test because she's only testing one worm. And if the worm is longer than 14 centimetres, then she is correct. So again, because she's saying it's longer than 8 centimetres, this is a one-tailed test. We're told that she's going to be rejecting her H0 if X is more than 14. This time, because it's normal and normal handles continuous probabilities, we don't have to change this at all. We can just put it straight into our calculator. In NCD, 14 is our lower, 9999999 is our upper, 4 is our standard deviation, and 8 is our mean, which gives us a probability of 0.0668. I would now like you to give the next Now You Try questions a go. So for the second Now You Try, we have Naya believes that a regular six-sided dice is unbiased, so that every number has an equal chance of being rolled. Again, this sounds like binomial, but we need to keep reading to check that we've got our set number of trials. She decides to test this by rolling the dice 10 times, so that's our number of trials, and records every time an even number comes up. So the even numbers on the dice are 2, 4 and 6. That's 3 out of the 6 options that there are, which is a half. So our probability is a half, so be careful there. She decides that if this happens less than 2 or more than 8 times, then her belief is incorrect. So she's going to reject H0 if it's less than 2 or more than 8. Now you could, again, find those probabilities separately by finding the probability of X being less than or equal to 1 and the probability of X being greater than or equal to 9. Remember that this time, when we're entering this into our calculator, for this one here, our lowest is 0 and our biggest is 1. And for this one, our lowest is 9 and our biggest is 10 because we only have 10 trials. And then we can add those two together and that gives us our alpha. But in the same way as I was talking about for the two-tailed normal distribution, if you think about our number line, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we are going to accept H0 if we have 2 all the way up to 8. So that bit there that I've just put in that box is my accept H0 region. Now, especially if you have the newer calculator, it's easier to find your accept H0 probability and take it off 1 to get your reject H0 probability. Again, it's up to you which one you want to do. So if we put that the lowest is 2 and the biggest is 8, and then if we do 1, take away that 0.9851562, we'll end up with the same answer again. It just depends which way you find it simpler. If you find finding the probabilities separately easier, then that's fine too. For our last Now You Try question, We've got Luke wants to perform a hypothesis test. He believes that the number of blue Smarties in a small packet of Smarties occurs at a constant average rate of less than 4 Smarties per pack. He decides that if 2 or less blue Smarties are in a pack, then his belief is correct. So this time he is including 2 in his reject H0 region. So if we were doing this as a hypothesis test, our H0 would be that lambda is 4, our H1 would be that lambda is less than 2. We're told in the question that we're rejecting H0 when we have 2 or less, so the probability of x being less than or equal to 2. So in PCD, our lower is 0, our upper is 2, our lambda is 4, and that gives us our alpha, which is 0.238. Remember again, if you have the old version of the calculator, your x will be 2 and your mu will be 4. So, next time we are going to move on to having a look at finding the probability of making a type 2 error. I just want to re-emphasise though that if you are given the significance level in the question, then that is your probability of making a type 1 error. If, however, you are not given the significance level, but you are given the criteria at which you are going to reject or even accept H0, then that is going to be what you're using to find out what your alpha is. If you are given the accept H0 region instead of the reject H0 region, then just remember that your reject H0 region is the other part of what your numbers are. So if it's a binomial, for instance, if we are told that we are going to accept it between 1 and 8, that means that we're going to reject it for 0 and more than 8. If it's Poisson and we're told that we're going to accept it if it is less than 9, then that means that we're going to reject it if it is greater than or equal to 10. If it is normal and we're told that we're going to accept it between 2 and 4, then we're going to reject it if it's less than 2 or if it's more than 4. Remember, normal is continuous, so you do not have to change the numbers when you are looking outside of it because we want to be including the decimals in there as well. Thank you very much for listening.